I'm co-organizing with Cindy, who's right there. So for SOAP this year, we have 3 keynote speakers and 8 talks. And the first keynote speaker is Eva Darulova, who's coming from Uppsala University, and she's going to talk to us about recent advances in floating point static analysis. Thank you, Eva.
Thank you for the introduction. Does it work with a mic? If I drop my hand, please just do me the favor and show me that I have to move it up. Okay, so I want to tell you about some of our latest work. So what are we talking about? Most of you will know what finite precision means, but just to make it clear, suppose that we're some kind of embedded engineer and we have some expression that may be, for example, an embedded controller that we need to implement on an actual computer. So the natural choice would be, for example, to use double floating point arithmetic, or maybe if we're concerned about resource consumption, we may choose single precision floating points. Now, at this point, many of you may already cringe a little. So we can just try to test our function, and let's take the double precision one and just use it with some random inputs. And if you do the math a little bit, not that you have to do right now, then this result would be the one that you would expect if you did this computation on paper. If we run this now in the single precision one, then we already get some of the artifacts that many people will expect with floating point numbers. So that result is clearly not quite accurate. But it gets a bit weirder. So if we take the double precision implementation and run it with single precision inputs, we get suddenly a number that is bigger than the result, no, smaller because it's a negative number, than the one that we would expect. We can take now the result, the first result here, and add it 3 times. And then we realize that that original result wasn't actually accurate. The inaccuracy was just hidden by the printing. What we can also do is take our floating point single precision computation and just rearrange the arithmetic a little bit. So on the reals, it's exactly the same thing. But if we now run our test input, we suddenly get the double precision result with single precision floating points. So at this point, if you're an engineer and look at this, you may wonder, well, how do I actually know that my results are good enough? Can I even trust them? So one way, we can always just throw in the towel and just say, well, we'll just have to trust it and just, believe. If this code is, however, running on some safety critical system, for example, on an airplane, then we may want to do better. So what we really want to have are rigorous correctness guarantees. So we can have a guarantee that our computations are good enough, at least for our applications. Now, the quote that I have there from Xavier Leroy is from a talk at Poppel in 2011. So you may ask, are we there yet? Do we have these correctness guarantees? Let me come back to this question at the end of the talk. What I would like to present today is a really quick background on floating point arithmetic and a sort of tutorial by example on today's main techniques for rounding error analysis. And then building on that, I want to discuss 2 of our recent work in pushing this rounding error analysis further. And really, this is work by my 2 PhD students. I was there helping a little bit. Okay, so let me start with the background. And this is mostly so that whatever I say later makes sense. So this is not complete in any way. So I'm assuming that we're talking about floating point numbers governed by the IEEE standard, and they're represented by a mantissa, that's basically the significant bits, and an exponent, that's the range of the number, the size of the number. And typically we talk about single precision, double precision numbers, maybe there is half precision these days as well. At least single and double precision floating points are typically supported by hardware, so that's what you will have on most computers. What we care about for arithmetic operations is that the standard specifies that these are computed as if we had real numbers and then rounded. So the rounding can be different. I will be assuming rounding to nearest, which is basically the default for most programming languages. Based on the definition of how arithmetic operations are rounded, we can use an abstraction that basically says this, that a floating point result is as if so a floating point number is as if we had it in real values, so that's without the tilde, with two different kinds of errors, where one error is for normal floating point numbers, that are the normal ones, and the d is for d-normal numbers that are very, very small. And then basically for different precisions, we have different values of the bound on these two errors, so the epsilon and the delta. The larger the precision, the smaller the error bound will be. There are also special values for floating points, like not a number infinity, but I'll mostly ignore these for this talk. One consequence of rounding is that floating point arithmetic is not associative or distributive, so the usual rules that you would expect on real numbers do not hold. So the results will not be the same because the rounding errors in both cases may be different. And then there are some additional identities, like we cannot dividing by 10 is not the same as multiplying by 0.1, and similarly here. What this means for our analysis, that we need to follow exactly the order of computation as is written as is basically written and will be executed, because if the order is different, the errors may be different. All right, so now we know about little bit about floating points. How can we bound rounding errors? So how can we compute automatically a guaranteed upper bound on these errors? And I'll be using this very simple expression through most or half of the talk. So we have a function with two inputs, and we just square them and add them. And importantly, we have bounds on both y and z. So these bounds are important because if these values would be unbounded, the error would be in general unbounded as well. So when we talk about rounding errors, it only makes sense if we talk about input bounds in most cases. So and then what I assume that we have this real valued specification, and then what we want to have is actually an implementation in floating points. So all inputs and all operations are floating point valued. And we may have some kind of input errors. And the goal is then to compute the difference between these two expressions, assuming that y and z are in the bounds as specified. Now, we have to compute an over-approximation. It is, especially for double precision, it's impossible to get the exact errors, so we can't just enumerate all of them. And the main challenge now is to compute accurate bounds. I can always give you a guaranteed error bound of infinity. It's going to be sound and correct, but completely useless. So basically the challenge is how close can we get to the true errors while still being guaranteed over-approximation. Now the expression as given here is too complex to reason about manually, automatically, at least today, because it combines real valued and floating point reasoning. So for example, we cannot simply phrase this as an SMT query. Well, I mean, we can, but the solver will not really give us any result. I'm talking here about absolute rounding errors. You may also ask, so what about relative errors? Let's stick to this because that's even harder. The relative errors are even harder. All right, so this is the thing that we're after, and it's complicated because it combines reals and floating points. So what we're going to do is use that abstraction from before and apply it to our expression. So if I take that f tilde, I'll make it now into an f hat, where all of the floating point variables and operations are replaced by this one. And I'm introducing new errors for each of them. So this is now very complex, but it is now only real valued. So there's no more mixing between floats and real theories, so it's only reals. But this is still too complex to reason about automatically for anything but very small expressions like this one. So what we need to do is basically find some ways of abstracting over this. And there's today, more or less, and I'm generalizing a little bit here, two approaches to rounding error analysis. One is data flow based and one is optimization based. So the data flow based will use data flow analysis with interval-like abstract domains So just to illustrate with an example, if we represent our example as an abstract syntax tree, we will track ranges of all of the variables because the errors depend on the ranges, and we will propagate them through the tree. And then we will similarly track the errors at every node, starting from the inputs, and then propagate them upwards through the tree. Now here I'm not telling you exactly how this propagation works, so this is governed by transfer functions that at this point are fairly well understood. So if we just have an addition, just to give you an idea, the errors get added. If you have a multiplication, it's a little bit more complicated. And basically the trick in this approach is to have abstract domains that are good enough so that you don't lose too many correlations between variables and error bounds remain accurate. The second approach is to take the definition of the absolute error and look at it as an optimization problem. What it is, where we're maximizing the difference, so that's an optimization problem. But it is too complex to solve as is. So what we need to do is simplify it a little bit further. And I'll tell you a little bit later how to do that, or one way to do this. And once we have done a little bit more simplification, then we can throw an optimization tool at it and actually compute a bound for the error. Any questions so far? Okay. So there's tools that exist today that implement one or mostly one of these approaches, and you can use them on some code. Typically, the data flow-based ones will be a bit faster, and typically the optimization-based one will give you tighter error bounds. It's not a hard cut, but that's the typical case. So there's no free lunch, if you will. The problem with both of these is that they're non-modular. So if you have a bigger piece of code with, for example, several function calls that are called several times, you will have to inline them and the whole thing will probably blow up in your face. They're also not particularly good at supporting loops beyond, again, unrolling and looking at straight line code. So, and that's the setup that we started off. So I want to now talk about our project about doing a modular analysis. And then after that, I'll talk a little bit about how we can do something about programs with loops. All right, so the first approach starts off from the optimization-based technique. And what I haven't told you yet is how do we do that first step so that we can actually use these optimization tools? Now, there's going to be a little bit of math. If you don't follow all of that math, that's fine. And I'll try to point out the really important parts of this math. So what we're going to do this simplification with is a Taylor approximation, which is a standard technique in math and physics to simplify complicated equations. So a first-order Taylor approximation of a function f, so that's our function f, looks as follows. So we evaluate f at a point that we choose. So we typically want to choose a point that works really well for our application. Then we take a first-order derivative with respect to some variables that we choose as well. And then we have a remainder that bounds the error. So basically we approximate f by a sum of terms. And by having this remainder, we then have a bound on how different this approximation is from the true function. Now, I'm talking here just about the first-order Taylor approximation. In physics, you may see several second order, third order, and so on. For our purpose, this is enough. So what we're going to do is we will compute a Taylor approximation of our f hat around the point yz 0, 0. So this is our suitably chosen point, which means that we choose a point where the variables e and d are all 0. So that means that's the point where we have no error. So that's this one here. And then we have a bunch of terms. So this is the Taylor approximation for the running example. Now this looks really complicated, but it really helps us because each term itself is simpler, and we can look at each term separately. So this is how we get the simplification. Each term will be simpler because we're taking the derivative with respect to our error variables, and they will typically not occur in the whole expression, but only in smaller parts. So in each term, much of that original expression will disappear. And that f hat of our suitably chosen point happens to be exactly the real valued function. So that means that when we plug this into our error expression at the bottom, this part and this part, at the beginning there will be the same. So we only end up with the derivative terms and that remainder. So the important thing is we're doing derivatives, and by doing so we get many terms, but each of the terms is simpler. So and once we have that, then we can apply our optimization technique. So just to summarize, what we're doing with our original error expression, we compute a floating point abstraction based on the IEEE standard. Then we use the Taylor approximation, computing derivatives symbolically. And then we can bound the individual terms using some interval domain. So we can either use standard interval arithmetic, or we can use more advanced techniques like branch and bound. Now this approach, and this is originally from the tool FP Taylor, this supports arithmetic and transcendental functions like sine and cosine. So we can easily do sine and cosine because for these we have derivatives that are well defined. So we have an abstraction step and we have an optimization step. Now this approach as is does not support function calls. So if you have function calls in your program, you have to inline them all. So, and this is what we want to avoid. So this is now our extension of this approach. So we start off, and I'm going to go through this with an example. So this is our running example. And now we will abstract the power function with a function call. Now, this is a very simple example for the sake of the talk. Typically, this one you would inline, but just for the sake of presentation. All right, so you will notice that the input range for our function g is large enough so it's safe to call g with both y and z. So their ranges are inside the range of g. I mean, that's the usual preconditions, if you wish. And I'm right now going to assume that we have no input errors, just to simplify the presentation, but we support them as well. All right, so our first step is going to be look at our functions that we have and compute error specifications for each procedure. So this will be some abstractions of what the errors will be that this function introduces, but without the full details. And I'm going to denote this error specification by the letter beta, with the subscript of the function that it belongs to. So this specifies somehow an upper bound on the error of that function. And then what we want to do is reuse that error specification when we compute the error so the error specification of g when we compute the error of f, so that we don't have to inline the full function. So once we have computed these error specs, then in the second step we will instantiate them with the appropriate context and actually compute the error bounds. The goal is to abstract enough, but not too much. So what does this mean? So we can abstract, so we can basically compute these specs as a constant error bound, but this will lose too much accuracy because notice, for example, in our, and I'm too short to point there, so when we call g with y, then y is much smaller than the full range of g. So the error that we compute if we just compute a constant bound for g will be much larger than what we actually get when we call g only with y. So we don't want to just have a constant. We want it to depend on the inputs somehow, a little bit at least. We can go to the other extreme and just pre-compute all of the derivatives and don't do any actual computation, but this will give us modest performance. This will just amount to essentially caching, a smart caching. So what we want is something in between. We want to pre-compute some parts that are suitable to be pre-computed, but not too much. All right, so how do we compute these error specs? We follow the rounding model and extend it with procedures. So basically we treat function calls or procedure calls as if there were an arithmetic operation that has an error attached. So if we take our example, then the G is the same as we had before with just the E's and D's. And now for the function called G, we express it as the real valued result of G, of the function, plus some error. And the error is exactly that error specification that we want. And this error specification depends on the input parameter. So it won't be just a constant, but it will be a function of the inputs. So the values of these symbolic variables are only needed at instantiation time in the second step. All right, so how do we... So once we have this abstraction, we will proceed as before with the Taylor approximation. So we will compute the derivatives with respect to the error variables, but now we will also compute the derivatives with respect to the error variables associated with the function calls. They're errors as well, so we do the same thing there as well, and we treat them symbolically here. And then here comes the abstraction part. We realize that some of these terms are actually typically very small because, for example, the errors due to denormal numbers are typically small as well. So we pre-compute them at this point using the full range, which does a bit of an over-approximation, but it's typically fairly small. So the part of the derivatives remain symbolic, and part of them we pre-compute at this point. And then, once we get to the second step, we instantiate all of the error terms with interval analysis. So we just plug in the values, the bounds that we know for the E's and the D's and so on. And now when we compute for the betas, then we use the actual intervals of the input variables of Y and Z. Now at this step we also check that we're not using a function whose range is smaller than the inputs, so that's a quick check. And the trade-off that we do here is that parts of these betas are computed with wider ranges than what is actually happening at the call site. But we do this computation only once. So we don't have a formal proof of the correctness, but we have a correctness argument that if you inline these error specifications without the pre-computation, then we get the same error expression as you would get with the regular inlining approach. So, a little bit of evaluation. There were no existing benchmarks for this, so we made some up with some matrix computation and some complex numbers. So we have a bunch of procedure calls. So obviously this approach is only useful if you have many procedure calls, because otherwise there's too much overhead of computing the error specs. Okay, that's the copy table from the paper, but let me give you the highlights. So Hugo, that's the name of the tool in the paper, just to make it different. So it is implemented within the DAISY framework. So that's the approach that I just talked about. Now, it's typically, if you have many function calls, the analysis will take significantly less time than DAISY's approach or the FP Taylor approach in the FP Taylor tool itself. So both DAISY and FP Taylor have to inline the function calls. And then for some larger benchmarks, FP Taylor times out after an hour. What we also get if, well, compared now to the error bounds with DAISY, they're actually, so if you compare these two numbers, they're much tighter than DAISY's error bounds, even though the analysis takes half the time, and this is because this approach uses the more accurate optimization-based approach and not the data flow analysis one. But we have made it scale up to actually work for these kind of programs. So that's the very short summary. Any questions? Okay, the remainder of the talk will have less math, promise. Yes. Yeah.
Are there like known error bounds, like theoretical worst case error bounds that you should be reaching here? Do we know how close the results that Hugo produces are to that?
Yes. So I do not have them there's two answers to this. So we can get an upper bound on the errors by doing testing. Okay. So just running the programs with many, many inputs.
Okay.
And this we would have to do on the inline function calls. I don't think we have done it for this one. Typically, these error bounds are within 1 or 2 orders of magnitude.
Okay.
But I'm just talking about my previous experience. We haven't actually done it here.
Thank you.
Have you looked at more complex call chains? So imagine not only f is calling g, but let's say f is calling g, is calling h, and so on. And for every function, you have more than one call site. So, for example, j might be called at with a very tight range and with a very wide range another position. Plus, you cannot just pre-compute it once because g might also be called by, let's say, f, which is called by a, and so on. Have you looked at these complex cases, and then what influence does this have on the parts that you do pre-compute? You said they are very small, but what happens if you kind of have so many call sites, some of them with larger boundaries? Shouldn't this add up then?
So as long as your call chains don't have loops, this will work. But this will mean that, so if your ranges vary a lot, then the approach will naturally always assume for the pre-computation the largest range. So you will get some over-approximation by this.
So there is no concept of saying, okay, if this is called more than, I don't know, 10 times, or with ranges that differ too much, then let's just not pre-compute it, because probably I'm losing too much precision, even if it may give me some additional performance.
Yeah, so we don't do this automatically. You could do it manually by basically having copies of the function. I guess that would be a sort of natural next step to do this. It wouldn't change anything in the approach, so that would be more, I guess, implementation and a bit of figuring out when do you split. You can mimic it manually by having copies of the function with different ranges.
It would be non-trivial to find out when to pre-compute and when not to pre-compute. Imagine you have like the full implementation of some flight controller. This can be a lot of code, and then you don't want to do this manually.
Yeah, no, so we don't know how to do that automatically.
Okay.
Hello. Just a general question about the input specifications. So I was wondering, like how much domain expertise you need to find like which inputs make sense.
Good question. Right now, we assume that the user will know. I mean, typically you would expect. So if this is an embedded system, then this would be the sensor inputs or something like this. And for that, I would assume the ranges are known. You would know what the specification of your sensor is. But we assume that the user knows.
And just one quick follow-up question. Could you also apply these to other kind of mathematical software, like, you know, like general math functions or something like that?
So if you talk about something like library functions,
Right.
like elementary functions, then I don't think this is the right approach. Just because the error bounds will not be good enough in that case. Also, for a library function, you have, I guess, more time to spend because you will do this once and then the function will be used in so many more contexts. So the techniques for these error bounds for sine, cosine, and so on, they're very different.
Okay.
So that's not the right approach.
Okay, thank you.
So I wonder where these benchmarks come from, or in general, what would be a good source of real-world benchmarks for this kind of work?
I wish someone could tell me. For now, basically everyone in the community is just making them up in some way, or you know, we pick them from. Some of these benchmarks come from embedded systems papers. There were actual proposed controllers. Some of these for the complex. The name tells you a little bit, so it computes an instant current. So they come from some codes that we found online from a physics application. But there is no standard benchmark set right now. I mean, there is one, but that does not have function calls. All right. Then let me continue with the second part. So I said a few slides back that we don't know how to do this analysis modularly, and the analyses are not particularly good about loops. So what about loops? They're tricky in general. So if we just take a very, very simple piece of code, programming language syntax doesn't matter, and I'm plotting here the actual errors with double precision, then you will see that typically these errors will grow with every loop iteration, but this growth is not necessarily monotonic. So it's complex. That's my main point. Natural in program verification, you would be looking for loop invariants typically to handle loops, but today we only know how to compute these for very special kinds of loops. So this is hard with floating points as well, mostly because of the complexity and because these errors tend to grow. So there's no simple upper bound you can find. But even if you just look at finite loops, then these are tricky because then we need to unroll them, and this unrolling scales poorly. So what we need is, or what we want, is effective abstractions. Again, there is two sides to this. We can always compute a trivial error bound of -infinity to infinity, but this will lose too much accuracy. Or we can do the naive unrolling, so we just unroll all of the loops, but this will have modest performance. So we're again looking at something in between. And we're going to look at very specific kinds of programs with loops, and I'm going to illustrate what we want to do with an example. So we have a timeline, we have a bunch of time steps, and what we're computing or simulating is a heat distribution. So initially we have an array, think of it as an array with values of temperatures of a rod or something like this. And then we want to compute the temperature after several time steps of the middle element. And the way this simulation works is we look at a sliding window of always 3 elements, and from these 3 we compute the temperature of the middle element at the next time step. And we basically do these for all. So we do the sliding window, and then in every step our array gets a little bit shorter that we look at, and then we continue in the next time step, and so on. Exactly what this application does is not so important. It's just that you have a little bit of idea of the computation that we're doing. So there is some kind of loop because we're doing this for several time steps. And there is another kind of loop because we're going through this, this array. So we can implement this computation, for example, in C. So this is syntax that we can run through the tool Fluctuat to actually compute an error bound using unrolling. So this will be naturally implemented with 2 for loops. Again, the exact details don't really matter. The point is there's 2 loops, and they're finite. We can unroll this completely and then run it through the tool Satire to get an error bound. But this will be 1021 lines of code. So that will take a while to analyze, even though the individual operations are relatively simple. So what we are proposing, what we are saying is, well, first of all, it's nicer to write this in a functional style. So this is the same computation written with, so this is a little bit syntactic sugar for the sliding window. This is a sum of elements, so this would be in functional style a fold. So we're writing this now in 6 lines of code, and we have no explicit indices, so we don't have a for loop that explicitly indexes into the arrays. So the vector data type there, think of it as an array, basically. So we are saying we should write this kind of code in this kind of functional style, and this also makes it easier to analyze the rounding errors, or at least it makes it faster. So we want to express these loops over data structures. So now I'm just talking about code that has some kind of vectors or matrices, and we want to use functional iterators. And then we will define an abstraction over the data structure elements, and I'll explain in a second what this means. But the whole goal of this abstraction is to avoid duplicate analysis. So for example, if we look at this, the computation, so that's the one that is done in each of these sliding windows, this is basically the same. And if our elements have the same range, then if we do unrolling, we're repeating duplicate computations. And this is the one that we want to avoid. The whole idea of using this kind of high-level language to express the code is to make it easier for our analysis to figure out exactly where this duplication happens. If we just have a simple for loop or completely unrolled code, we would have to reverse engineer this information. But here we get it right from the code. I'll have more examples of this later. So just to give you an idea what we get from this, so this particular example we can analyze in much shorter time than the other two tools. At the same time, we don't get the tightest error bound. So that's the cost for the abstraction. We can do the analysis faster. We will compute slightly looser error bounds. All right, so the whole approach is implemented within DAISY, but it's called DS2L, so that's also the branch where you will find the implementation. And it basically consists of this functional DSL over data structures, an abstraction of these data structures, and then transfer function so that we can use, this time, the data flow rounding error analysis. And let me just give you a very quick overview. So the functional DSL that we propose, though the point is really just to demonstrate that the information we get from this DSL is useful. So we have real valued vectors or matrices. There's no matrix in this one. And then the input specifications will provide a maximum size of the data structure. So this is interpreted as the maximum number of elements. And we provide ranges for each element. We can also provide some sub-ranges where the elements have different values. And then there are some operations that we currently support, and this is basically, we looked at a bunch of applications that we found online and made the DSL work for these. So we can use the regular higher order functions, map, filter, and fold, and the sum here is just a fold with some syntactic sugar on top. We have some element-wise operations, so these are two vectors that get multiplied element-wise. We have a few domain-specific functions that can be expressed as maps and zips and so on, but they're nicer to write like this. And then we have a few non-numerical operations, so we can get the length of an array so that we can actually have a loop. So the second loop here is expressed as a recursive function, but that one will be unrolled implicitly. All right, so then just to give you a quick idea of the abstraction that we want to have. So suppose that we have a vector v, and we're mapping over it and adding 3.5 to every element, and then we get the result stored in an array R. So, and now suppose that some of these elements have 0 to 1 range, and the others are 2.5 to 4. So when we do, so this means that we can have only two different results of adding 3.5. If we unroll, we have to do this computation 8, 10 times. But really what we really only need to do is to do this computation twice. We only need to look at one of these green elements and one of the orange or yellow elements. Similarly for the error analysis, we only have to compute the errors once for the green and once for the orange ones. And that's basically what we're doing. So our abstraction will group these data structure elements by their range and then do the error analysis only once for each of these ranges. These ranges don't need to be consecutive, so we just look at the indices in there. And then the actual error computation is reduced to a straight line data flow analysis. So we reuse the existing approach, the second one from that overview slide. But the point is that we use the semantic information from the input DSL to figure out how often do we really need to do this error analysis and only do it once. And then the data flow analysis we just do with simple interval arithmetic. All right, so in the end we get our expected result. So this was just for the ranges, and then similarly we do that for the errors. Now, this is obviously hiding a lot of details here, but this is the core idea. Now, we again had to make up some of the benchmarks. So these were found online by my student, Anastasia. And we tried to make them diverse in the sense to cover several different applications. But I have no claim that this is exhaustive in any way. So our main goal was scalability. So if you look at large benchmarks where basically the data structures are big, so we have to do large loops with many iterations up to 708K, then our approach basically handles many more of these benchmarks. So we can handle 67%, whereas the other two tools can do less than a fourth of these. So if the other two tools do compute the result, then our approach is also several x faster. Again, there's no free lunch, so our errors are a bit more loose. So compared to Fluctuat's, ours are about twice as big. They are comparable to Satire's approach. So are we there yet? I would say that if we have just pure arithmetic, straight line, no loops, no conditionals, and so on, probably yes. So there's tools that can do that, and the list is not exhaustive. Are we there in terms of scalability? Maybe, maybe not. Are we there? So I've completely hidden any discussion about conditional statements. That's because they're tricky. So if we have a conditional statement like this, so we have some arithmetic computation, and then we compare the result against some kind of threshold. Now the problem here is that our real valued execution may now take a different branch than the floating point implementation will. So we get an error, an additional error due to basically divergence of control flow. Now if the code is simple as this, we can handle it already today, but anything more complex, I don't think we really know how to do that. And then the loops, I'm leaving that box open as well. So we can handle some kind of loops, so there's different approaches for different kind of loops. But for general loops, say for a simulation of the Jupiter orbiting the sun or something like this, I don't think we can really do much yet. But I think we can do better than the garbage times garbage approach. And that's what I wanted to say. Thank you.
Thank you very much, Eva. One more question.
Very interesting. Can we make some sort of constructive approach out of that? Like rewrite the code, simulate again, but not in a like shotgun approach. I just change something and see whether my bound gets tighter. But from the bounds analysis, get an idea of what to change to make it tighter, and then hopefully have some sort of iteration that gradually gets us to as close to the real numbers as we could get. Because I think that could be very fascinating, especially then when you also look at the, for example, time and memory requirements. If you're talking about constrained microcontrollers like flight operation controllers, I mean, these are usually not x64 chips with all the memory in the world. But if you have an approach where you say, okay, these are my hardware bounds, and now let's get the best out of it, that would be awesome.
So if you have resource bounds, so if you have limited resources, you probably do not want to get close to the reals, but you want to reduce your precision as much as possible so that your results still remain accurate. So then you probably don't want to use double floating point precision, but you want to use 16-bit fixed points or something like this.
Yeah, my idea was more like you can compute the error bounds, but you have already shown that even if I just change the formula slightly in the code, this can make a difference. So if I say, I know that I can't just bump up the precision, I can't just go to double precision, could your approach be used to say, hey, this is code, please do optimize it. I have to stay with single point precision, but please rewrite my code in such a way that I'm getting the most out of it.
So some of this our tool does already. So if you have straight line, we have an optimization tool, optimization approach, and there are other tools that implement this as well that do this kind of rewriting. There is, as far as I know, no analytical solution for this. So the problem is NP-hard. So it's all heuristics. So we basically try different rewritings and rerun our analysis and try to find the one with the smallest error bound. But this is an heuristic search. So if you have a short straight line code, this can be done already. That said, typically the improvements will not be huge unless you have a cancellation error, so a really bad way of writing your codes. We can discuss offline a little bit more. But if you don't have this kind of cancellation, then typically what we have seen are improvements of 50% of the error bounds, so maybe not even an order of magnitude. So there's not that much. So you can do a little bit, but not that much.
Thanks. I really like this idea about the specification for the loops. But you had shown that you have two different bounds. Sorry. Do you assume equal distribution about those two?
Equal distribution of what? Sorry.
That they both happen equally often, because it seems like in the example you had half of them with the one distribution, half of them for the other distribution.
That was just by chance. So you can, in the specification of the bounds for the data structure elements, you can either say they all have the same range, or you can specify every individually, or anything in between.
Oh, okay. And this specification, I assume this is not pretty easy for people to write. Do you think there's one way to automatically infer this from the code?
I guess this is a similar question than Cindy had. So this kind of static analysis will basically work on relatively short pieces, even if you can do some procedure calls. So we had some previous work where we looked at even larger pieces of code, say 2,000 lines of code. And then this whole arithmetic operation still be hidden somewhere in some function deep in the call stack. And it's only that one that we really want to analyze. But we do need these ranges. So there we use the dynamic analysis to help us find an under approximation of these ranges. I'm not aware of a static analysis that actually worked.
No, I think I was referring not to the ranges, but to the specification. It seems to me the specification needs to be written by hand.
Yes, exactly. But for that specification, you need the ranges of the inputs.
Yeah, but the functional style, is that possible to infer somehow from the imperative program?
That doesn't change the fact that you have to specify the ranges, but maybe I'm misunderstanding the...
That's two different problems.
Yeah.
Okay.
One last question.
Hi, kind of an outsider's question, but so I see that you compute, tighter or looser error bounds. At some point at a higher level, this has to relate to some kind of assertion that you can either prove or not prove, right? Like some correctness property about the software. I don't know if there are, maybe this relates to the benchmark questions. It seems like that's the bottom line question, right? Not necessarily whether you can prove the tightest possible error bound, but whether it's good enough to prove your correctness property. Can you give some intuition on the connection and whether these error bounds are almost good enough, or no, we need to do way better to prove the assertions that we care about?
Yeah, I probably can't give you a very good answer because it will depend on the application. So for example, if you're looking at an embedded controller, then the error bounds that you can compute, or the rounding errors, will influence the stability of the controller. If your errors are smaller, there will be a larger range where the controller will be stable. Now, what is good enough will depend on, for example, the proof of stability of your controller. Out of that, you typically assume some kind of noise term that will tell you, the thing is going to be safe as long as, your error is not bigger than this. And then that depends. So I don't think we can say that, if we're on the order of 10 to the 12, then it's good enough. It really depends on the application.
Okay, let's thank Eva again.